Hi, my name is Brian Caffo. I'm a professor in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is the Coursera lecture on inference and regression in the data science track. This course, the regression class, is co-taught by my collaborators Jeff Leake and Roger Pang. So let's just take a minute to review our model and our how we fit it. So our model is this guy right here, where yi is beta naught plus beta 1 xi plus an error term. We're going to assume that the errors are IID, normal, 0, sigma squared, and we're going to assume that the that the true model is known, not the parameters, but at least that this model formulation with the sampling model is all correct, and that what we're missing is that we don't know beta naught, we don't know beta 1, and we don't know sigma squared. And I'm going to assume that you've seen confidence intervals and hypothesis tests before. And then recall, under this model, the maximum likelihood estimates work out to be beta naught here as y bar minus beta 1 hat x bar, and beta 1 as the correlation times the ratio of the standard deviations. Okay, so let me, just because this guy is a little bit small, let me rewrite it a little bit bigger. So if we have an estimator theta hat, and we subtract off its true value, theta, and divide by its standard error, sigma of theta hat, right? So that's the square root of the variance of theta hat. That often has a normal distribution, normal 0, 1 distribution for large sample sizes. If there's some sort of IID-ness built into the problem somewhere, like our IID errors. And then often if we replace that sigma with its estimated version for small sample sizes, for large sample sizes that also tends to be normally distributed. And often for smaller sample sizes it tends to be t-distributed if we have assumed normality at some point. But the t-distribution has nice fat tails, so assuming a t-distribution often isn't the worst thing to do anyway. Okay, so it is normally it's often normally distributed and has a finite student's t-distribution as the estimated variance is replaced by the sample variance, and we can use that to test or create to test things like theta equal to theta naught versus some of these alternatives. Like what I mean is HA theta greater than theta naught, or HA theta less than theta naught, or HA theta not equal to theta naught. Okay, let me get rid of all that stuff just because it's clouding things up a little bit. And then we can also use it to create a confidence interval for theta, and our confidence intervals usually look like theta hat plus or minus an appropriate quantile times the estimated standard error, where the appropriate quantile is, you have this distribution, and we want it so that alpha over 2 is in the upper tail, so 1 minus alpha over 2 is in the lower tail. And that quantile is Q 1 minus alpha over 2, and usually this is either a t or a normal distribution. And then, so when you took your inference class with IID sampling assumptions and Gaussian errors, our inferences are going to just follow what you saw in your inference class. In fact, all of the intervals we covered in the inference class for continuous group data, for example, the two-group t-test, they can all be viewed as sort of special cases of these regression type estimates. And we're not going to cover asymptotics for regression analysis because you have to make some assumptions about how the X process is going to infinity as well. If you have bivariate Gaussianity, then it's certainly no problem. Or if you have an instance like ANOVA or something like that, where the X's are specified into groups with some assumptions about how the X's go to infinity within the groups, then you're fine. But that's maybe a bit much. Suffice it to say, then under very relatively broad settings, the asymptotic normality will also help you, and there you don't need, actually need normality of the errors. You just need the sampling assumption that they're IID, and some assumptions about how x is going to infinity. Those two things will give you all the asymptotics you need. And when we switch over to generalized linear models, that's what we'll take advantage of. But we're not going to cover that because it's a bit advanced. Okay, so let's derive the variance of the slope coefficient just to show you how these calculations are done. It's a lot easier if you actually know the linear algebra, but in this case we can do it pretty simply on our own. So what we want is the variance of beta 1 hat. And then in this line right here, all I've done is replaced beta 1 hat with its estimator. Then remember that because summation yi minus y bar equals 0 and summation xi minus x bar equals 0, that we could write summation xi minus x bar yi minus y bar, we could write that either as summation xi minus x bar times yi, or as summation yi minus y bar times xi. Either of those works. You can work out the arithmetic. So we can get rid of one of the bars, x bar or y bar, and we get rid of those, and we come down to the next line. Oh, and then if you pull this whole guy, which remember we're conditioning on all the x's, if we pull it out of the variance calculation, it gets squared. Okay, so that we're at that line right now. Now the yi's are all independent. They're not identically distributed because they have different means, but they're independent, so we can move the variance across the sum. And when we do, if we pull the xi minus x bar part out, it gets squared, and variance of yi is sigma squared, so we get that. Sigma squared doesn't depend on I. And then what we'll have, I'll just rewrite this right here. We have sigma squared summation xi minus x bar quantity squared over summation xi minus x bar squared quantity squared, and that cancels with one of those, and we wind up with this expression right there. Okay, so again, that's just for people who enjoy those kinds of details. Otherwise, what you could say is, okay, well, here's the variance for beta 1 hat, and then you could do the same sort of exercise and derive the variance for beta naught hat. And of course, we don't actually know sigma, so we replace it by its estimate. And then under IID Gaussian errors, this expression, the beta j hat minus beta j over its estimated standard error, follows a t distribution in n minus 2 degrees of freedom. So if you're used to the single group t-test, then you'll have noticed we lost an extra degree of freedom because we have to estimate one extra thing than we normally do. And then for a large n, it follows a normal distribution, and you can use this to create confidence intervals and perform hypothesis tests that you already know how to do at this point. So let's go through the diamond data set one more time. So again, here's loading the data and getting the correct library. I'm just defining the x and y's and n's just to avoid having to type the $sign. We could type LM and get beta, but of course we can always just define beta the old-fashioned way. Since we know how to do it on our own, we could get beta 0 as the mean, as this definition, mean y minus beta 1 mean x. We could define our residuals this way. We could get our estimated residual variance as the average squared residuals, but we're going to get our nice unbiased estimate, we'll divide by n minus 2 instead of n. So instead of the average residual, we'll divide by n minus 2. I just for notation's sake, the sum of the x's minus their means squared, I'm going to just call SSX for sum of the squared x's. Okay? And then my standard error for beta naught is this guy. If I plug into my formula, my standard error for beta is sigma over square root SSX. And then I'm saying that my t distribution for beta naught for a hypothesis test of h naught beta 0 equals 0. Why would I write beta? H naught beta 0 equal to 0 versus HA beta 0 either greater than, less than, or not equal to 0, then that would be this t statistic right there, and then there's our t statistic for beta 1. And then if we wanted a p-value, we want the probability. Let me just draw it. Let's say for beta 0, if we wanted a p-value, we'd want, if our statistic was positive, we'd want to take that area from the t distribution and then multiply it by 2. If our statistic were negative, we'd want to take that area and multiply it by 2. So kind of the easy way to do that is to just take the absolute value of the statistic and say lower tail equals false. Or if you didn't even want to write absolute lower tail equals false, you could just force to get the negative one by putting a negative sign out front. Just make sure that degrees of freedom are n minus 2. You want to multiply your p-values by 2. If you get a number bigger than 1, then you've taken the wrong area, right? You've gotten the, instead of getting the small part of the tail, you got the big part of the distribution. We could do the same thing for beta 1 right there. And so, here I just create a little table of all these values, and then I add the names for them as the estimate, standard error, t-value, the probability, and so on. Okay, there we go. And here's the result of those calculations. Now, of course, we don't do this when we actually create these kinds of tables. We instead just grab them from LM, right? So summary. So here I'm just fitting y as outcome, x as the predictor. Summary of fit will print out lots of stuff, but it doesn't fit on my page. So I'm just grabbing the relevant output from summary fit. $ coefficients grabs the table, the t table. So here's the intersect column, here's the x column, and you can see, of course, we get the same exact numbers, so our formulas are right, and apparently we implemented them correctly, right? So they all agree. So that's how R gets that stuff, and so now you could get it too. So I think at this point you should be able to program, the vast majority of what LM does, you should just be able to program from scratch if you wanted to. And then getting a confidence interval. You could, let's see, as a confidence interval, let's see, so if you want to grab the coefficients, you can do summary fit and then coefficients. That'll grab the table, and then the relevant elements of the table are the 1, 1 for the intercept, and then 1, 2 for the standard deviation of the intercept. I need to grab the correct t quantile, and then I want to add and subtract it, so I just multiply by c, -1, +1, and that gives me a confidence interval, and that gives me a confidence interval for beta 1. And so just to interpret that confidence interval, we're 95% confident that 0.1 carat increase in diamond size results in a 355 to 388 increase in Singapore dollars. Of course, once again, just like in the previous lecture, probably a 1 carat increase, as this is expressed, is probably too large, so we want to divide it by 10. Okay. Let's consider predicting a value of y at x, but doing it in an inferential way, not just giving a prediction. You already know how to get a prediction. So, as example, from the two examples we've covered, we might want to predict the price of a diamond given the mass, or we might want to predict the height of the child given the height of the parents. So the obvious estimate for a prediction at a point x naught, we've already talked about this, is just beta naught hat plus beta 1 hat x naught. But if you actually want a prediction interval, right, something that incorporates the uncertainty associated with that interval, you need a standard error, okay, and some knowledge of what the distribution of the prediction estimate. is to create an interval. There's a kind of subtle distinction between, I guess what I would say, intervals for the regression line at point x naught and a prediction of what a y would be at point x naught. And I think a picture will help describe this. So at any rate, for the line, we get this standard error right, or this, this standard error right there. And you can plug directly into it. And for the prediction interval, you get this standard error. And the only thing different, right, is that 1 right there. So you get a wider interval for the prediction interval. So let's see what it does. We'll go through our code, and then we'll see what it does, and I think you'll understand it better. So here I'm generating a plot of my x and y's, and I have all my my little settings I like there. I'm going to add a fitted regression line. Here's my x values that I want to predict at, and my y values that are my predictions, beta naught plus beta 1. Or remember, I defined beta naught and beta 1 previously. So those are the coefficient values. I'm giving my 2 standard errors, and then I'm going to plot my lines. Notice what I did when I did this, the collection of values I wanted to predict at. It's a dense grid from between the minimum observed mass and the maximum observed mass. So I'm plotting the prediction lines on a prediction estimates on a very fine scale, and then I'm going to plot all these lines. The plus two, and I'm being lazy. I should use the appropriate t quantile, but I'm just putting 2 in there because for a Gaussian, the 97.5th quantile is 1.96. That's around 2. The t quantile should be a little bit larger. So I'm being lazy. I should put in there QT, right, 0.975, and the appropriate degrees of freedom is n-2. Right, I should do that, but I didn't do that. And in fact, it didn't save any time because I just spent all this time describing it. So one thing to notice, the width of the prediction interval, right, it's not constant, right? It's gonna let's see, if you look at it, right, look at the prediction interval width here, or I'm sorry, the regression line interval width here and the prediction interval width there. That function is going to be lowest when the x values are at or near the mean, right? Because this term right here is just going to drop out, right? So your prediction interval is going to be narrowest at the mean, and it's going to increase as you go away from the mean, right? So that's exactly what we see. It's a little bit hard to see on this picture. It's maybe easier to see on the regression line picture. But if we were to say, which makes total sense, but if we were to say predict a point way out here where we haven't observed any data, the prediction lines bow out a lot more. Okay, so here's the difference between predicting the regression line at that point and versus the prediction interval at that point. See how well these points generally fall on the line. We're pretty confident we have the line, right? Maybe not perfectly, but we have it pretty well, right? I mean, those points fall pretty well on that line. So we know we've got the line really well estimated. Okay? So if what we wanted to estimate is what is the value of that line at that particular point, right? We don't actually have a lot of uncertainty, right? We may have messed up the line by a little bit, but not by much. Not by much, right? And you can think as you get more and more data points, we're going to get a better and better estimate of that line, right? And so the variability associated with the prediction should decrease, right? And if you look at our formula, right, what happens? Well, you have this term that's going to tell us, well, if you're far away from the average of the x's, you're going to have a little bit worse prediction. But then there's this other term, right, 1 over n. As we get more and more data, right, that goes to 0. Right, that goes to 0. So if we're predicting at the average, right, as we collect more and more data, that interval is going to go to 0. In contrast, look at the prediction interval. It has this part 1 that doesn't decrease with n, that's just intrinsic, that never goes away, right? And that's, so the prediction interval is these lines right here. So if instead of saying what's the line at 0.3, I wanted to say I want to guess what a particular y value is at 0.3, well then you have to include all this uncertainty for the points around the line. If we collect an infinite amount of data, that's not going to change the amount of variation in these points. The infinite amount of data is going to change the amount of variation in how good the estimate is of the line itself. And as we're saying, if we want to predict the point at a line, then we're going to do quite well and the interval goes to 0. But if we don't, right? If we want to predict the point, well then we have to incorporate the uncertainty associated with all the points around the line. And you can see these prediction lines for the prediction interval, not the expected value at a point x interval. They kind of encompass the variability of the points themselves. So most of the points kind of lie close enough, lie within the prediction interval. So that prediction interval incorporates that uncertainty of the points around the line, whereas the prediction for the line at that specific point only is concerned with how well have we estimated that line. And so for the prediction interval, another way to think about it, right? For the prediction interval, there's three parts, right? There's sort of like this part that says, well, how close to the average are we relative to the variability of the x's? That kind of talks about how close to the middle of the data you are, where you should get good prediction, right? This part kind of is added on, sort of relates to how good is our estimate of the line, right? So both these parts, both those parts go to 0 as, both these parts go to 0 as you collect an infinite amount of data. And then there's this part right here, the 1, that just never goes away as you collect more and more data, and that just says how much variability is there around the line. And I just to reiterate, that makes a lot of sense. If our regression points fall, like with this amount of variability, right, around the line, right, it makes sense that if we collect, let's say we collect 100 billion data points, well, we should get that line pretty well, right? We should get that line pretty well. But what we'll never get rid of is the fact that the points fall randomly around the line, so that if we want to incorporate that uncertainty into our prediction, we use one interval, or if we just want to predict what's the line at that specific value, then we use a different interval. So to me, it makes a lot of sense, and that's why there's two different intervals. Okay, so just to discuss these points on the slides. So both intervals have varying widths depending on how close to the center of the data you are relative to the variability of the data, the x's. So in our specific case, we're quite confident in the regression line, so that interval is very narrow. And in fact, another way to think about it is if we actually knew beta naught and beta 1, this interval would have 0 width, right? We would know exactly what it is. However, the prediction interval must incorporate the variability in the data around the line. So even if we knew beta naught and beta 1, that interval would still have width, just the residual variance around the line. Okay, so that's why we get two different lines. So how do we do this in R without having to actually manually do the predictions? There's this nice function predict, and you guys are all hackers. You should be able to figure out how to use it. You have to define new data. It has to be in a data frame, and your definition of your interval will tell you the width of the interval and so on, which are the two kinds of intervals it does. And here you can see just I did it, and you get the same picture. One last thing I want to point about standard errors that I maybe forgot to point out earlier is the slope standard error, right? The standard error for the slope. I should have pointed out this earlier. When is this variance of beta 1 the lowest? Well, you want variability in your x's, right? That's an important fact. I want to make sure we emphasize that. You want variability in your x's because it decreases your variability in your slope, right? And that makes a lot of sense. How well are you going to be able to estimate a regression slope if you collect data all right in a little cluster, right? Very little variability in my x's, there's going to be a lot of variability in my regression slope, okay? But on the other hand, if I collect data nice and spread out, right, then I'm going to get a better estimate of my regression slope. And it turns out the maximum amount of variability that you can get, by the way, is the following. Take half your points and put them very low, and half your points and put them very high. And as much separation as you can get in these two things, and you want these to be all even at the same point, as much separation as you can get in those, then the better your line estimate is. Now, I'm wondering if anyone can see the problem with that strategy if you were to, say, design data collection. Well, ultimately the problem with that strategy is you got to be very certain that this linear relationship holds between your two sets of points, right? You're quite confident at your average y value there, and you're quite confident at your average y value there because you collected a lot of data at both those points. But if the relationship is something like that in between, then you've totally messed it up. And not only have you messed it up, but you haven't collected any data to evaluate that problem, right? Residual plot would show nothing, right? You've only collected two different values of the x's. But at any rate, so I think people intuitively, if they were to design an experiment, wouldn't dump all their data at one point and at another x point like that unless they were quite sure of the linear relationship. People wouldn't do that intuitively. But what's more important is just this idea that if you want to investigate regression relationships, what's important is to have lots of variability in your x's and little variability in your y's. That's the ideal circumstance, right? What's the best circumstance? You have all your data points falling on a nice line or close to a nice line, and your x is nice and variable. That's the best point. And that's when we think of a regression, like a really nice regression data set, that's what it looks like, right? The x variation relative to the residual variation, relative to the x variation is being very small. And that's what we think of when we think of a great, sort of very nicely fitting regression line that should be well estimated. And I think the diamond example is an example that looks pretty much like that. To me, that's, what hopefully I don't know a lot about diamonds, so I don't know if this range of carats is the right, is a good amount of variability in the x's, but there isn't that much residual variability. So it looks like a nice regression relationship, and that's what it's saying. So it is nice that all our formulas exactly mirror our intuition.